Hey Danielle,
Hey, I just wanted to apologize about the misunderstanding.
that's okay. Don't worry about it. I
Okay,
it said all that stuff in the syllabus, but I know students don't necessarily want, even if they do read it, they're not going to have it memorized or anything like that. So it's fine. I actually set it up to take as late as today anyway, so you're all good.
is it okay if I take it tomorrow evening because I have the lab tonight?
Yeah, that's fine.
Okay, thank you so
Hey, with your
much.
proctor, is it okay with your proctor?
Oh yeah, it's okay with her.
Okay, no problem. As long as it's cool with her and you, I'm good with it. Good luck on it.
Thank you so much.
You're welcome. Hey Carter, how's it going?
There we go. Good. How are you?
All right. Just doing my thing, trying to keep up with the class, all that good stuff. Uh, always something.
Always something.
Half the time I forget to make a duplicate of my notes, and then I end up not having anything ready when the next class starts. But this time I remember because I am Mr. Teacher.
Did you have you I don't know how close you've been following that Mrs. Ashby story, but I saw something uh recently that like somebody was like had I don't know had brought out their dog and claimed it was like a scent sniffing dog and he wasn't. And like they like lost resources and stuff and like a few days
Oh,
of searching because he had like claimed a bunch of stuff that like wasn't true.
that's terrible. That's not
Yeah.
helpful.
No,
Yeah, I actually heard something about someone had found a woman walking down the street and helped her, but they were out in the middle of the country. They didn't really have any phone service or anything like that, but took them back, got them warm, dressed, and then we're going to report them, but it never came of anything. So I don't know if that was just completely made up, but I was hoping for a bit there that would have been her.
yeah.
But yeah, she's got a stepdaughter and her daughter and husband and many people that just love her, and it's just terrible to think that she's probably gone.
Yeah, it's awful.
Yeah, first time I ever had anybody that I know that was lost in a storm.
Hmm.
Uh,
Yeah,
yeah,
and it was such a crazy thing because everyone was so worried about Florida, and then all of a sudden, they got the middle of North Carolina, and it's just awful.
exactly. The same thing, well, I say the same thing, a much lighter version of the same thing happened to me when I first came to grad school at Chapel Hill. I had just finished at East Carolina, and we moved from Greenville to Chapel Hill, and the storm was so minor I slept right through it. It wasn't a big deal at all. Well, that turned out to be the one that was so bad in Greenville and destroyed
Hmm.
everything. Like I
Hmm.
looked, and my apartment was on the national news, and it was an upstairs apartment, and a boat was up, had pulled up to the upstairs window. That's how
Wow,
the water was.
that's crazy.
Yeah, but I completely slept through the storm because it was so minor. But I got up and we were without power for, I think we were out of power for 10 days. They're just not prepared for that. And not only that, the ground in the mountainous regions isn't very good at absorbing dirt and not having a problem with it. So there was just a ton of trees down and all sorts of crazy stuff.
That's crazy.
But yeah, East Carolina ended up beating the Miami Hurricanes, who were a top 10 team at the time, but they were on suspension, so they weren't actually technically allowed to attend a bowl, but we still beat them right after it. So, yay.
Hey, there you go.
I don't think we've had a impressive win since then, to be honest with you, though. You have any questions on stuff we've done to date?
No, I texted you. I have some test questions, but I'll wait till the test is locked out.
Okay. Yeah, I actually got like 15 texts today, so now I gotta sort through those. A bunch of them are politics, so that's a pain in the butt. I keep hitting stop to end, and they say you've been removed from the list, and then I get 14 other emails.
Yeah, never matters. They
Yeah,
find you somehow.
yeah, exactly. They can tell because I'm so rich. And they know I
Yeah,
give all this billions of dollars. I'm just like, Elon.
yeah. They're just waiting for you to donate. It'll change their campaign.
Yeah, I'm gonna donate my 75 million and then give $1 million a day for people that register to vote.
Yep.
Fix it. We got about 1 minute left. Anybody else have any questions?
Yes, I had a quick question.
Go for it, Tanika.
In regards to the test, was the formula sheet not supposed to
Ah,
be on the test?
I was looking for your email earlier. I couldn't remember if it was an email or a text you had sent
It
me.
was the text message.
It was supposed to be in the book, but I also had provided the proctors with copies and stuff like that in case they needed it. Uh, was yours not, did yours not have a copy of the equations in it?
I had the physics one equations in the front and back of the book. So I didn't have the physics two equations, which I was like, I had it for the practice test. What's that?
Yeah, you're
So
supposed to. If you'd like a retest, you can totally do it. If you just
mhm.
find a time to fit it in, I'll give you a retest. You just let me
Yes,
know when
that
you
I
want
will
to.
appreciate that
And I'll give you the
tremendously.
higher of the two because that's my screw up.
Okay, thank you.
No problem. Just let me know when you want to do it. I'll set it up at the testing center and you just show up when you can and do it. And like I said, I'll give you the higher of the two test grades.
Okay, thank you so much. They'll have a physical copy of it, or will it be in the exam?
It will be in the exam as well as if you want to bring a physical copy, you're allowed to. I send them a copy. Well, I send proctors a copy so they can know what a valid equation looks like. Uh,
Mhm.
if I send it to the testing center, they might actually print it out for you so you'd have a print copy too.
Okay.
And by the way, Tanika,
Wow.
I suspect if Tanika had that problem, many of you did. So if anybody wants to do that, I'm completely on board with letting y'all take another poke because I didn't give you the equations. Luckily, I had a lot of students that brought their own equation sheet, but if you didn't, you had a disadvantage. So I certainly understand you wanting to retake, and I can do that. I'm going to make up a different test, but it'll be sort of the same level of difficulty, the same concepts, and all that good stuff. Anybody else? If y'all are that way, I'd recommend. Well, normally I'd say text me, but I got 15 texts there. But I still think that's the best way. So text me if y'all need that, and we'll just find a way to work it out. I've since put the actual equation sheets in it. I don't know how it ended up only having the 241 one. I think maybe it got erased one time because when I go to edit the test. It's a pain if I put in new questions because I have to go up over all of those documents. So I end up erasing all those documents and then putting them back after I'm finished editing the test. But sometimes when I re-put them back, I think I put them all back and I didn't. So that must have been what happened. Anybody else have any questions? Okay, so far two people have went ahead and chatted me your first and last name. So everybody go ahead and do that. And Hannah should be able to hear me now. She was the last person that just logged in. So I think now everybody can hear me. I wanted to make an announcement. I'm shooting for a test that will be available next week. I haven't decided whether I'm going to make it available and then be due, at Sunday of next week, or if I'm going to make it due maybe Wednesday of next week or the week after next or something like that. But my intent is sometime today or tomorrow to put up a practice test for the next face-to-face test. And then you'll have a face-to-face test coming. It'll definitely be release sometime next week. It's just a matter of I'm not sure if I'm just going to give you till Sunday to get it done, or if I'm going to give you till the following Sunday, or till Thursday or Wednesday or something like that. So I just wanted to make that note clear to everybody. So a test is coming up, a face-to-face test. We're going to get my intent is to get three of those. If I get three, then I can justify personally my desire to drop one and not feel bad about it. If I get four, I will drop one as well. If I get five, sometimes I even drop two at five. But that's what I'm shooting for, is at least getting three. And by doing that, like I said, it allows me to drop your lowest one, and everybody will capitalize on that. Additionally, something else I just announced, and not everybody was necessarily here. One student advised me that she took her test and didn't have the actual equation sheet because it only had the 241 equation sheet in the test, and she didn't personally bring her own copy, which she didn't have to. She wasn't supposed to necessarily, but she was welcome to. So I've decided anybody else that had that problem and didn't have an actual, equation sheet with them so that they could take the test as well as they would like to, I have to let y'all take another attempt. So I've already got one person. I advised her to let me know date and time that she wants to go to the testing center. She'll try to make an appointment at the testing center for that date and time, and I'll set up the arrangement once we know that that date and time works. And I'll do that for anybody else that has it too. If you had your own equation sheet, then you shouldn't take advantage of this. But if you didn't have your own equation sheet, you were at a disadvantage, and I certainly understand it. If you didn't feel that disadvantage, you can choose to take it again or not. It doesn't matter. It's up to you. But we are getting ready to have our second test, and that's going to be at least on the next two chapters. I haven't decided whether to be 2 chapters, 3 chapters, or 4 chapters, but it'll at least be on the next 2 chapters. The last one we did was 17, 18, 19, 20. So the next one will at least be 21 and 22. And that's the 2 major announcements I wanted to say. We're going to go ahead into chapter 22. Again, anybody have any last minute questions before we get started?
I noticed that the 17 through 20 face-to-face practice test closed on Saturday, and I didn't realize that. I did the chapter 20 face-to-face practice test
Gotcha.
instead. Is that like equivalent, or do I need to do both to like get the extra credit? Or
No, the only ones that matter are the ones that are in the practice test. And when I wrote that one that said 20 only, that wasn't even one that was required to take. So if you got a chance to get 100 on the previous 3 practice tests, you get your 100 period. Doesn't matter. The tests do though. That's the key point of the practice test. If I have a practice test, for instance, for a test that's supposed to happen by Sunday of next week, then that means the practice test will disappear Sunday of next week, because I'm giving extra credit for people taking it because I want them to take it before they take the actual test. I'm not going to give them any extra credit for taking it after the test. So that's why I make the test disappear.
okay, yeah, I was just wondering because it had closed before it had closed before the test was due.
Yeah, that's not good. Well, it's good, but it's not good. I went in and reopened it when I basically set up. I basically went to this testing center and sent them an application for my online classes and allowed them to take it up through today. And then I reopened the practice test again. I suspect you got it during that period that it was closed, but it had been reopened. I'm sorry that happened, but you probably did the best thing you could by studying the chapter 20 ones. Of course, that just gave you chapter 20, so that's not that helpful. What I can do, I'll double check and see what my dates were, and if you missed it specifically because of that and didn't have any attempts on it, then I can give you another chance to do better on that practice test.
Okay, thank you.
You're welcome. Yeah, I'll open it up for like another day or something, and you can try to get your 100 on it. But like I said, as long as you got something other than 100, you're going to get partial extra credit for it. But if you get 100, then you can get the whole 5 points as long as you get 100 on every one of them. All right, so we are going into the chapter called Electric Potential, and that's chapter 23 of your textbook. And we're starting off with that. So I'm going to go ahead and explain to you what chapter 23 is about. So when you did 241, and evidently it's impossible to adjust a hat while on Zoom because it's got your mirror reversed like this. So every time I do it, it gets like that, and it just looks stupid. So I don't even know why I'm wearing it at this point. It just looks hideous. Oh, okay, that's good. Okay, OCD in me is strong. So when we did 241, you had Newton's laws of motion. You had Newton's first law, Newton's second law, Newton's third law, and Newton's second law was the summation of the forces is equal to mass times acceleration, which is a vector equation. And you saw that really in order to do that, you had to make a free body diagram. You had to break all the force vectors up into components parallel to the x-axis and parallel to the y-axis. And sometimes you even tilted the x and y-axis, and then you had to adjust it, those vectors such that they had components parallel to those axes. So it was a little bit of work, and it took a little bit of trial and tribulation and difficulties to solve problems. So you might have asked yourself, God, is there an easier way? And then chapter 7 came along, and that's when I introduced the concept of work. And then chapter 8 came along, and that's when I introduced the concept of conservation of energy, because it turns out that work and energy are both scalar quantities. And essentially, you can do just about everything that you do with Newton's laws and vectors, you can do with the energy equation. Now, I've made up sort of this internal conservation law that I've just found to be true, and I don't know that I could actually prove it or anything like that. But what I have discovered is when you find neat little tricks like that that save you trouble, it's almost, or at least every time I've seen it, this happens. So, for instance, when you go to solve a problem using Newton's second law and you want to solve for the acceleration is sort of about the easiest thing you could do. Specifically, you're going to take all the forces and get them on the left-hand side of the summation of forces equals mass times acceleration. And then you put mass on the right-hand side and the acceleration on the left-hand side. And as a vector, that allows you to solve for A. And immediately you get the acceleration. Pretty straightforward. Again, you still have to use vectors, but it's pretty straightforward. It turns out if you switch into this new paradigm where you're going to use scalars, it turns out the acceleration is kind of hard to solve for. But the thing that's really kind of hard to solve for in the vector way was like finding the final velocity or finding the time or something like that. Those, once you have the acceleration, then you have to put in a kinematic equation. You have to put in the initial velocity. That gives you a way to calculate the final velocity. You have to do that for all the components. So velocity is more of a pain than acceleration, and time is equally as much a pain. Well, it turns out in the conservation of energy methods, the velocity is really easy to get. That's the first variable you solve for, because one side of the equation has 1/2 mv initial squared, and the other side of the equation has 1/2 mv final squared. So you end up getting v final immediately. So what I've found is, if you find something really hard in the vector way, that might be really easy in the conservation of energy way. But if you find something really hard in the conservation of energy way, that might be very easier in the vector way. And that's held true my whole life. So I think there's some truth to that. It's even worked in like quantum mechanics where sometimes you have to solve a differential equation, and a differential equation is sort of the hardest thing to solve. But there's a way where you can avoid solving the differential equation, and then you just have to do a series of derivatives. When you do that, what you find out is the actual part of it's easy, but the other part's hard. So even in quantum mechanics, it works. And I just stopped you guys from being subjected to a pointless rant about quantum mechanics. But luckily, I've become a smarter teacher, and I know not to do that necessarily. So what I'm going to do is now I'm going to introduce an idea, specifically potential energy, which you already know about. And there's a way where we can incorporate that into electricity and magnetism. And it parallels what we did with Coulomb's law of force, then making it Coulomb's law of the electric field. So let's get started by sharing my screen. So I'm going to share my iPad screen. And I'm going to remind you that what we learned early in 241, right after we finished chapter 6, for instance, we went into chapter 7 and 8, we learned that you can actually do conservation of energy, but there had to be very specific types of force. Specifically, the types of force were conservative. Okay, I told you, those people that had me, I told you all that conservative forces are ones whose quantity called curl is equal to 0. And then that became equivalent to basically there exists a scalar potential, and that scalar potential can be related to the electric field by E equals the negative gradient of the scalar potential. If you integrate a path from A to B, that actual result of that integral will just be a function of the endpoint minus a function of the initial point. and it doesn't matter what path you choose. Another thing was if you integrate in a circle, you're always going to get 0. All those things became equivalent. So it was kind of a neat little thing. And now what we're learning is it turns out, since Coulomb's law looks just like the law of gravity, remember gravity being G m1 m2 over r squared, and Coulomb's law for force is K Q1 Q2 over r squared. They look identical. So as you might have guessed, since the gravitational force was conservative, then clearly the Coulomb force is going to be conservative. And because of that, we can create a scalar potential. It turns out that the scalar potential that we're going to make is what we call voltage. Okay. So what we did, refreshing your memory, is we had force, and force was a good quantity. Specifically, we had force is equal to K. I'm using K just because that's easier, times Q1 times Q2 over R squared. And we found that that was a bit of a problem because of action at a distance. It was also a problem because it wasn't a vector equation, and we remedied that. But the big thing was it was flirting with action at a distance. In other words, it was almost as if one charge, let's say Q1, reached out across space and grabbed a hold of Q2 to apply a force to it, only there wasn't anything connecting Q1 and Q2, so that couldn't be the case. That's what we call action at a distance. So what we imagine is, imagine if Q1 was considered to be the source of an aura, and that aura became known as our electric field. And then you treat Q2 as something, since it's a charge, it could in principle create an aura as well, but you're treating it in this case as if it's the thing feeling the aura. So the way you could find out the effect of the aura without the Q2 was you would say there's a quantity called E, and that E was F divided by Q2, which gave us, of course, K Q1 over R squared. And of course, because we were dealing with Q2 by logic, if Q1 can create an aura, then Q2 can also create an aura. So how do you deal with that? Well, in principle, the equation is just E equals F over Q. But in practice, if you really want to try to do this, what you would want to do is take a limit as Q2 gets smaller and smaller, so that it has no effect on the existing electric field. Because what's really going to happen is Q1 is going to create electric field, Q2 is going to create electric field. Those two electric fields are going to combine to create a net electric field. But what we want to do is look at that electric field as if we're subtracting out the effects of Q2. And the way we do that is we look at the total electric field when Q1 and Q2 are there, and then we shrink Q2 a little bit, look at it again, shrink Q2 a little bit, look at it again, shrink Q2 a little bit, and keep doing that. So we just took a limit, in other words. Okay. So that actually did fix it. And it turned out that ultimately we were able to measure an electric field that was ultimately something that we could actually, in some sense, measure in the lab. So we actually had those carbon sheets, and they allowed us to find equal potential lines. Once we found the equal potential lines, by the way, that means equal voltage lines. In other words, each one of those equal potential lines was a line that had a specific voltage, and the other line would be a different voltage, and the other line would be a different voltage again. So that's what we were doing there. And then the electric field was perpendicular to those equal potential lines, right? So now we're going to try to work with potential energy. And what you might remember, you might not, but the change in potential energy, delta U, which is UB minus UA, when we use A and B, A comes before B in the alphabet, so the B would be recognized as the end, and the A would be recognized as the beginning. So that's why I wanted to take time to show you that's what delta U was. But what we found was delta U was equal to the negative of the work done in going from A to B. Okay, I would have written this AB, but your book seems to be writing this as BA. Okay, so I'm just trying to, let me double check that too. I might be remembering the other book I'm using. Yeah, they did use that. They used B to A. Okay. So this was exactly what we used to define potential energy. So this defined potential energy. So that's how, after we had work, that was how we got to conservation of energy, because we needed different types of energy, one of which was kinetic energy, another one was potential energy. And then we actually found out that there were different types of kinetic energy as well. What I want to remind you of is this work that we're talking here about here is the work done by the conservative force. Okay, that's key there. That's, that's part of the reason why we have to put the negative there and that sort of thing. So the change in potential energy is always defined to be the negative of the work done by the conservative force that creates the potential energy. Remember, you have to have a conservative force in order to create in order to create a potential energy. And that's what we're doing here. So that's what I'm starting off with. Now, remember, I advised you that we were going to do something analogous to what we did with force and the electric field. So to go from force to the electric field, we divided by a charge. We treated one charge as the source and then the other charge as the thing feeling it. So I'm going to do the same thing now. I'm going to introduce a quantity, and this quantity is going to be called delta V, which is VB minus VA. And what that's going to be is delta U divided by Q, which is also equal to UB minus UA over Q, which you could also write UB over Q minus UA over Q. And that's what we're going to do. This quantity is called the electric potential. Notice I stop at the word potential. I said it is the electric potential. R voltage. And from this, you should see that the units of delta V, which is also the units of V, has to be equal to the units of potential energy divided by the unit of charge, like that. So we get the joule per coulomb. That's the unit that we expect for this quantity that we're calling voltage, just based on the way I just defined it. Okay. Now we go further with that and say that 1 joule per coulomb is equal to 1 volt. And that's exactly right. Now we could write that as VOLT, but the abbreviation is also just 1 capital V. So that's our electric potential. You could call the delta V the potential difference. So this would be called the potential difference. But notice we never use the word energy when we're talking about that, because this is a different quantity than potential energy. If you throw the word energy on the end, then all of a sudden everybody says, wow, well, that better come out in units of joules, and we want units of volts. So that's why it's not going to do that. Now, with our idea of this stuff that I just wrote out in that long blue equation, I can now relate that to work. Remember, work was equal to the integral of F dot dl. So I can now say delta V, which is VB minus VA, which is actually equal to the negative, actually, I should say, is actually equal to UB minus UA, oops, over Q. But UB minus UA is delta U. So that's delta U over Q. And then I can go back and say that delta U is the negative of the work done against the conservative force divided by Q. Okay. So now I can use that and realize that from the equation right here, everybody see that right there? That equation gives us another equation, specifically F is equal to QE, like that. So that's what I'm going to put in for W, I mean for the F and W. So I'm going to say delta V, which is all that stuff I just wrote, is negative W over Q. So that's going to be negative integral. Now, in place of F, I'm going to put Q times E, and then I'm going to dot that with DL like this. And then all that, of course, is going to be under Q. Now, Q in general is a constant. So this is just going to become the negative integral of E dot DL. And that is our defining equation. Okay. So our defining equation is delta V, which you can think of as VB minus VA, is equal to the negative integral of E dot DL from A to B. Okay, so that is the fundamental equation that defines what our electric potential is. And of course, these other things that I found work as well. So for instance, one of the findings I have from all of this stuff right here is that delta U is equal to Q times delta V. That is, in fact, another equation that is always true. So this is a valid equation, period. If you can find the change in voltage from one point to another, then the change in potential energy is just the charge times that change in electric potential. So those are sort of the most fundamental equations that we have right now. What I want to do now is show you an actual example. So first off, what we can do is I'm going to, just to make it straightforward, I'm going to create a coordinate system. You can do your own coordinate system in general, but what we're looking at is specifically a capacitance problem. So what I'm going to do here is I'm going to draw one side of a capacitor. Now, you don't necessarily know what a capacitor is, but you did study them in your electric field lab, specifically when we put two rods next to each other, two of those little metal things on the carbon paper next to each other, and then it had a little wire running to the outside edge. That was essentially like a capacitor. So what I'm going to do is put two of those, and I'm going to recognize that this one is due to the positive charges, and this one is going to be due to negative charges. So ultimately, what I'm going to do is box them off like that. And they're supposed to be rectangles, but it's not that big a deal. Now, what I'm going to do is say this has a positive charge, a positive charge, a positive charge, a positive charge, and this one will have exactly the same amount of negative charge. Okay. Now I'm going to say this distance right here is D. Okay. I don't like how that turned out. So that's D right there. And inside of it, what we did learn, hopefully to some extent, between the electric field mapping and then when I used Gauss's law to calculate the electric field above an infinitely large plate. We found that the electric field above an infinitely large plate of uniform charge density, sigma, was sigma over 2 epsilon naught. And when we put a positive plate next to a negative plate, right in between those two plates, the electric field for the positive plate pointed to the right, and the electric field for the negative plate also pointed to the right. So you end up getting sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which gave us sigma over epsilon naught. Therefore, the electric field between these plates is a constant. So what I'm going to do is draw this electric field, and really electric field lines are supposed to be pictured as being created at positive charges and disappearing at negative charges. Okay, so this electric field, we're just going to say is E. We know it's a constant, so I'll write constant. And I'll put a vector symbol over it just to remind us it is a vector quantity. Now I'm going to create my axes. So I'm going to draw a vertical axis right here. I'm going to draw a vertical axis right here. That's going to be my y-axis. And then I'm going to draw a horizontal axis right here. That's going to be my x-axis. And then, of course, you can also see that that spot right there is clearly D. And this spot right here, oops, this spot right here is clearly the origin. Okay, so what I would like to do is calculate the difference in electric potential of these two spots. In other words, I'm going to imagine, for instance, taking a particle and putting it right here. Let's say a blue particle. I'm going to put it right here, and then I'm going to imagine moving it over to this side. So that's what I'm going to try to do, and that charge is going to be a lowercase q. So this charge will be a lowercase q, and we're imagining moving it from left to right, from specifically from x equals 0 to x equals d. Okay, so our problem is, what is delta V? And I'm going to say this point right here is A, and I'm going to say this point right here is B. So I'm going to say VB minus VA. Okay. Now, what we learned was that delta V is equal to negative integral E dot dl from A to B. Okay. And that, of course, is also equal to VB minus VA, which in our case is V capital B minus V capital A. Okay. Now, I can do this, and this particular integral is what we call a path or a line integral. It's a little bit more advanced than just a run-of-the-mill integral. And that's a branch of mathematics that, unless you took my particular section of 241 when you took it, you might not be familiar with it at all. Okay. It's covered in Calc 3, but to be honest with you, I've never been at a university where they managed to get to line integrals and surface integrals in Calc 3. So I don't know how often they do it, but I do know it exists in the back of the textbook. So you can actually find the material there. But I'll warn you, mathematicians do line integrals and surface integrals a lot different from the way we do in physics. They're both equivalent. I've learned how to do both of them, but just be advised it'll look a lot different, especially the line integrals. Surface integrals aren't too terrible. So let's go ahead and compute this. I want to calculate what the difference in voltage is. I don't necessarily know what the voltage at the positive side is or what the voltage at the negative side is, but that's typical because, as you learned in 241, it's really the change in potential energy that matters. In this case, it's really the change in electric potential that matters. So we're going to go ahead and calculate that. So what I'm going to say is my electric field is equal to some constant, but it points in the positive x direction. So I'm going to put it with an I hat. I am going to move from A to B, and A corresponds to, let's say, x comma y is equal to 0, 0 for A, and then for B, it's going to be D 0. Like that. That's where I'm really going. So when you actually do a line integral, like I'm getting ready to do here, you have a choice. You can use the limits of integration, for instance, the A to B, to indicate which direction you're going, or you can use the DL to indicate which direction you're going. So either A and B indicates the direction, or DL indicates the direction. If you're not using DL to indicate the direction, then DL should just point in the positive coordinate direction. Similarly, if you're not using A and B in the limits of integration to show the direction of integration, then you should just go from the low coordinate value to the high coordinate value. In other words, in the positive direction again. So a lot of times you're not even going to know it if you don't do the line integral right, because it'll just automatically fix itself. In this case, you'll sort of see that. So what I'm going to do is, in this case, I'm going to say, let DL show direction. Okay. So what I'm going to do is, since I'm using the DL to show direction, then I'm going to not use the limits of integration. So the limits of integration just need to go from small value, which is x equals 0, to large value, which is D. And then I have E is specifically, E vector is E times I hat, where E is a constant. And then your DL is going to be positive DX. And then that's pointing in the I hat direction. So that positive sign right there is where I'm telling the mathematical machine, but I'm also telling you guys that we're going from left to right in the positive X direction. But notice, if I had also done it with the range of integration, then I would have made from 0 to D, and then the DL would be DX I hat, the same. So you would have got the right answer either way. Wouldn't have mattered. It's not always that way, as you'll see in a second. So now I can do this, and what we know about the dot product is it's called a linear operator. So I'm going to pull out the E and the DX. They're actually scalars multiplied by the vector. So the linearity of the dot product allows me to pull all the scalars out in front and then just let the dot product act on the vectors. In this case, the E is a constant, so I'm not only pulling it out to the front, I'm pulling it out in front of the integral. So this is going to be from 0 to D, and then the dx is still behind the integral, but then I have I hat dot I hat, which is, remember, A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. In this case, that means a hat vector has a length of 1. The other hat vector also has a length of 1. These two vectors are identical, so the angle between them is 0 degrees. And of course, the cosine of 0 is 1. So the whole dot product gives you 1 there. And what we end up getting is delta V is equal to negative E times, now we have the integral of dx is just x, and I got to evaluate that from 0 to D. So I'm going to say it's negative ED minus negative E times 0, which is just 0. So our delta V is equal to negative ED. Now, the fact that that's negative means specifically, since the electric field goes from the positive side to the negative side, I went in the direction the electric field points. And that electric field always points in a direction of decreasing voltage. So that's why it came out to be negative. You can always still use the result of delta V equals E times D, but this is only true for a uniform electric field. So I'm going to say R delta V equals E D, but again, only true for, I don't like the way I did it, only true for uniform electric fields. And I'll say uniform is also constant. Okay, so those two equations are valid, but they're only valid for uniform electric fields. So that was not really an example your book chose to do, but it's a result that your book just took and said, this is it, and wrote it down. Now, if you want to know the potential energy, now you can say, well, delta U is equal to, well, let me write it the way that I defined it. Delta V is equal to delta U over Q. So that means delta U is equal to Q delta V. So if you actually want to know now what the change in potential energy is, for this particular case, you're going to get delta U is equal to Q times E times D. And again, this is strictly for uniform electric fields. So I'm going to put this sentence right here. And I'm going to point it to that one, to that one, and to that one. Okay. Now this will come in handy. For instance, notice that's an energy delta U is equal to a charge times a voltage. And that allows us to introduce a new unit. So a new unit for energy. And this is specifically used when we're dealing with protons, electrons, neutrons, those kind of things. The unit is the electron volt. And that's abbreviated lowercase e, uppercase v. Okay. What I'll tell you is that 1 electron volt is defined to be the energy delta U that you get from letting 1 electron, which has a charge of 1.602 times 10 to the negative 19th coulombs. Now notice I'm using this equation right here. Okay, so there's the Q. And what I'm also doing is I'm saying that the voltage, which by the way, this part right here is the voltage. So it's more this part that I'm using here. Electron going through a potential difference of 1 volt gives me 1.602 times 10 to the negative 19th. And remember, the definition of a volt is that it's a joule per coulomb. So when I multiply the volt times a coulomb, I just get a joule. So this is a quantity that you'll be expected to know how to use every now and then. And it is one of those conversion factors that you'll find in the front cover of the book, which is supposed to be at the bottom of your test. Anybody have any questions on that part? Okay, so your book does a conceptual example. I think that's a really good conceptual example. So I'm going to sort of try to mimic it as best I can in a way that hopefully is not offensive to copyright law. So I'm going to call this conceptual example. Well, wasn't that neat the way that happened, jerk? So this is a conceptual example. Now, what I'm wanting to look at here is it says, suppose a negative charge such as an electron is placed near the negative plate in the figure below at B. If the electron is free to move, will its electric potential energy increase or decrease? So I'm going to make out that problem and say, if the electron is free to move, that turned out good, will its potential energy increase or decrease? So that's what we're asking. Let me draw the diagram now. So the diagram, we only need a small part of it. And I'm going to do it like this. Okay. And what I'm going to do is I'm going to say that I have a plus charge, a plus charge, and a plus charge. I have a minus charge, a minus charge, and a minus charge. And what we're going to say is that the electron is right here. So that's our point. Actually, your book is calling it point lowercase b. So I'm going to say that's lowercase b, and I'll say this is lowercase a. Okay. Now the electric field, remember, goes from the positive sign to the negative sign, like that. So there's our electric field, which is a constant, of course. So really what we're asking here is, which direction is the electron going to move? Anybody tell me? I've got it right there at B. Is it comfortable there? Can anybody tell me that? Is that negative charge comfortable right there at B that I have drawn?
No, it's not.
It's not. It's almost as uncomfortable as, for instance, the typical example that I use over and over, almost as uncomfortable as a turtle on top of a fence post, right? And the higher the fence post, the more awful it would be. In this case, it's sort of the same thing. It's almost kind of opposite though, but specifically, the thing that is trying to pull the electron is the positive charges. So the positive charges are sort of acting like gravity pulling on the electron to the left. Because those negative charges repel the electron, it's wanting to move to the left. So yes, it's not comfortable there. And therefore, is it going to move to the right or to the left? Carter or anybody else for that matter?
To move to the left, to the positive.
Exactly. So I'll say, well, first I'll erase a bunch of stuff and then complain about it. So the electron is uncomfortable at B because like charges repel. So the electron will move to A. Okay, so if the electron actually does move to A, what we need to know then is, has the potential energy increased or decreased? So delta U is supposed to be what we found before was Q delta V. Okay, that's one way of looking at it. And if we actually knew the voltages and stuff like that, it would be helpful. But what we do know, based on what we just worked out ourselves, is that this side is high voltage and this side is low. Okay. So basically what happened is I took a negative charge, negative 1.602 times 10 to the negative 19th coulombs, and I moved from a low voltage to a high voltage. So my final voltage is actually a high voltage and my initial voltage is a low voltage. So I'm going to say big number minus small number. That means that delta U is in fact less than 0. So the potential energy actually decreased. Does everybody follow that? Because delta U is less than 0. Does that make sense to everyone? Now, this is kind of a big deal, so it really needs to make sense. It's not one of the things that you just want to say, well, I don't necessarily understand it. I'm sure I'll figure it out later. This is sort of what helps you do all the stuff in the future. What you have to realize is objects naturally go from high potential energy to low potential energy, meaning that they do that all on their own. They don't necessarily have to be pushed. They're just going to do that naturally if they can. Now, you know, if you put, for instance, a turtle up on top of a telephone pole or up on top of a fence post, then obviously he's going to have some help to get started. But instead, if you put, let's say, a basketball on the top of a sharply peaked hill, even though it's smooth but still sharply peaked, it's really hard to balance that basketball at the very peak of that hill without it rolling one way or the other, and therefore of its own is probably going to roll down the hill and decrease its potential energy. So what we see in this case is the electron did in fact do that. It went from a high electric potential to a low electric potential, and because the change in potential energy is Q times the change in electric potential, and Q is negative, we got a delta U was negative. So we do see that the electron does act like normal particles. It moves in the direction of decreasing potential energy. But here's the weird part. It moves in the direction of increasing electric potential. So that's another thing they should do. I would write it somewhere. Negative charges move from high potential energy to low potential energy, but they also move from low electric potential to high electric potential. And that means from low voltage to high voltage. And that also means from negative to positive. So try to write that down, or try to fast forward to this point in the video and come back and write it later. We're 12 minutes after 6 right now, so that should give you a rough idea where it is. But electrons, like everything else, goes from low potential energy, or excuse me, from high potential energy to low potential energy. But unlike positive particles, they move from low voltage to high voltage, which is low electric potential, to high electric potential, which is from negative voltage to positive voltage. So they actually literally, you would picture the electrons as if they're coming out of the negative side of a battery, going around the circuit, and then coming in the positive side of a battery. Any questions on that? All right, so that was a big deal. That gives you some fundamental stuff to think about. So I want you to think about it. And your book says, caution, a negative charge has high potential energy when potential V is low. So that's what they're saying, is it goes from low potential to high potential. Now, if we go on, your book does a neat little thing with table 23.1. I do want you to look at that. That gives you some typical voltages that you encounter in everyday life. So for instance, lightning typically has a voltage of roughly 100 million volts. Power lines, these are the ones that are on those big towers that go through, country fields, and they look like sort of people with shoulders but no arms and no head. Those big towers carry really, they call them high tension lines, but those things are normally at hundreds of thousands of volts or even millions of volts. So 1 million, 1.2 million, something like that. A typical car ignition will run on 10,000 volts. A household outlet, we know those are 125 is what we call them. That's called the root mean square. An automobile battery technically is a 12-volt battery. A flashlight battery, so your double A's, triple A's, C's, D batteries, those are all 1.5 volts. Of course, the 9-volt batteries, guess what? They're 9 volts. But another neat thing is the resting potential across a nerve membrane is about 1/10 of a volt. So literally tenths of a volt, we can actually detect that with our multimeters and voltmeters, and that's really the action potential across the nerve membrane. If you want to look at the action potential on the actual skin due to EKG or EEG or ECG, by the way, in the medical field, they call ECG and EKG about the same thing. EEG is a different one. That's the electroencephalogram. So that's about your brain. But those things reach 10 to the -4th volt. So like 1/10 of a millivolt. So it's worthwhile for you to know that that's a typical voltage to deal with. Here's another example we're going to try to work and see if y'all can make any sense of it. So I'm going to call this example 2. Actually, I'll call it example 23, 2. So what we have here is I'm going to draw a plate. And this plate, in fact, is uniformly charged negative, like this. And then some distance away, there is another plate, and that plate is positively charged. And what you'd see on that one is basically a positive charge of a uniform amount on each side, like this. Now, in the middle of it, there's going to be a hole. Okay, because what's going to happen is we're going to have a little electron right here. There's our E minus. And of course, the E minus is going to be compelled to move to the right because it's wanting to be repelled by those negative charges. We're going to say that the voltage difference between these is actually, I'm going to make it high voltage. So basically, what we're doing is we're going to put a really high voltage on the green one, on the one with the positive charges, and then the one with the negative charges, we could essentially connect that to ground. That would be fine. What I'm going to do, though, is I'm going to say that this is 8,000 volts. Okay. And what does that mean? That means, let's draw a multimeter so you can get a feel for this. So here's our multimeter. And here's our little screen. Here's our dial, which is going to be set to V. And it's got those straight lines over it, so you know it's VDC. We have a COM port right here. And we have a V omega port right here. So what I'm going to do is I'm going to take this V port and connect that to the metal plate there. And then I'm going to take the COM port and I'm going to connect that to the metal plate as well. And lo and behold, what it's going to read is 8,000 volts. Okay. So that's literally what that means, being positive 8,000 volts is the high voltage. Is I'm telling you the high side is the plus side and the low side is the minus side. And what we want to know is what is the change in potential energy? So A delta U is equal to question mark. B, what is the final kinetic energy? And C, what is the speed, the final of the electron? Okay. So what we know is that delta U is equal to Q times delta V. And that is a valid equation that happens to work here. I didn't have to use the fact that the electric field was uniform or anything else like that to make that the case. We also realize that the voltage at the initial point is 0 and the voltage at the final point is 5,000. So we can make use of that. So let's get started with part A. I'm going to say delta U, which is U final minus U initial, is equal to charge. That's 1.602 times 10 to the negative 19th coulombs, and that's a negative charge. So I had to put that negative sign in there. Now, you don't necessarily have to put that negative sign in there, but if they really wanted to know exactly the change in potential energy, then you need to know the sign as well. Okay. If they just wanted to know how big the change in potential energy was, then you could just take the magnitude. So that's the charge. And now the change in voltage would be, final voltage would be 5,000. No, 8,000, excuse me. The final voltage would be 8,000 volts minus the initial voltage, which should be 0. And really all we know by doing it this way with that multimeter is the difference between the negative and the positive is 8,000. The negative could be at 400 and then the positive would be at 8,400. But the main thing is I'm showing V final minus V initial. Okay. So when I do that, when I actually multiply negative 1.602 times 10 to the negative 19th times 8,000, I get negative 1.28 times 10 to the negative 15th joules, and that is the change in potential energy. So the electron really is moving in its natural way. It's going the direction of decreasing electric potential energy, or excuse me, just potential energy, but you could call electric potential energy because it's clearly electric that caused it. Now I can do part B, which is what is the kinetic energy final? Well, what we can do is we can either use the way that your book mostly used or the way that I used. Remember, my conservation of energy was U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. That was the way I taught my students to do conservation of energy, but you can also do delta U plus delta K is just equal to 0. And then we have to ignore things like work put out, work put in, and E loss. We have to either not solve those problems or we have to pretend that those amounts are negligible. So I'm going to use the second one. And what we know is delta U is equal to negative 1.28 times 10 to the negative 15th joules, plus now delta K is K final minus K initial, and that's all equal to 0. But this electron started at rest, so I'll say E minus started at rest, which implies V initial is equal to 0. And that also implies K initial is equal to 0. So we now can say that K final is equal to basically positive 1.28 times 10 to the negative 15 joules. And that's what they wanted to know, is what is that kinetic energy? So I'm going to leave that in black, and I'm going to circle it off with red. Now, the other part is C. They want to know what is the final velocity. So kinetic energy, in this case, K final, is 1/2 m V final squared, and that's all equal to 1.28 times 10 to the negative 15th joules. So we can find that V final would have to be the square root of 2 times 1.28 times 10 to the negative 15 joules divided by m, and the mass of the electron, I happen to know, is 9.109 times 10 to the negative 31. By the way, when they do a problem like this, they often give you the mass of the electron, but also in my tests, I have the masses of the electrons and protons and all that. That's all in the front cover of the book, and therefore at the bottom of the test. So when I compute all this, what I'm going to do is take the square root of parentheses 2 times 1.28 10 to the negative 15 divided by, I'm going to do another, no, I don't need another set of parentheses. I'm going to say 9.109 times 10 to the negative 31. And now I'm going to close parentheses. All that's under the square root, just like I want it. And that gives me V final is equal to 5.30 times 10 to the, and now we got to watch out, 1, 2, 3, 4, 5, 6, 7. That's 10 to the 7th meters per second. Remember, the speed of light is 3 times 10 to the 8th meters per second. So V final over C is equal to 5.30 times 10 to the 7th meters per second over 3.0 times 10 to the 8th meters per second. That gives me 0.1767. So I'm at 17% of the speed of light. Anytime you come within, even really 1% of the speed of light, you should be using relativity, to be honest with you. So this kinetic energy formula is not technically the right one to use for this particular voltage, just because that came up so high. Anybody have any questions on that? If, in case you wanted to know, the correct kinetic energy formula is gamma minus 1 times mc squared for the actual electron, where gamma is equal to 1 over the square root of 1 minus v over c squared, like that. So you'd actually have to compute that gamma, subtract 1 from it, then multiply it by the electron's mass, and then multiply it by the square of the speed of light, and that'll come out in actual units of kinetic energy. But in this case, we have the K, the M, the C, and we'd be needing to solve for V, so you could do it that way as well. Anybody have any questions on that one? Okay, so that's a very typical type of problem that you should be able to do using this new concept of voltage, electric potential, that sort of thing, but also making use of specifically potential energy as well. So we have a potential energy that we're used to from gravity. Remember, we used mgh, or in certain cases, we use U equals negative gm, meaning the mass of the Earth, over R. That was the potential energy, but it had to be negative when you're dealing with objects roughly a distance away from the Earth that's comparable to the radius of the Earth. So, 2 or 3 multiples, that sort of thing. Then you have to use that formula. So now we've got a potential energy associated with electricity, and that one turns out to be Q times delta V. So we need to look at some other things and specifically figure out how we can use these equations to work problems. So let's do another example. This is going to be example 23-3 in this case. Okay. What I'm going to have again is a parallel plate capacitor like this. And with the parallel plate capacitor, I'm going to say that the separation distance from here to here is going to be, let's make this 7.5 centimeters. Okay. And I'm going to say that our multimeter would read a electric potential difference of delta V is equal to, let's say, 100.0 volts. Okay. So we're saying basically one side is positive and then the other side is equally negative, like this. So what that means is the left side is 100 volts higher than the right side. And what we want to do is determine the magnitude of the electric field between the plates. Now here we already know that the electric field between these plates is a constant. And since it's a constant, that means a uniform electric field. And we know specifically this information. Actually, I'm going to write that in red. So we know that when E is uniform, our constant, then delta V is equal to E times D. Okay. Now, technically speaking, we had signs and stuff like that, but we're really looking for a magnitude here. So all I got to do is I'm going to say that's 100.0 volts is equal to E times. Now I got to take this centimeters and convert that to meters, which means I got to move the decimal 2 places to the left. So I'm going to call that 0.075 meters, like that. And all of a sudden we've got a new unit for the electric field, which we sort of had already, but now we can see it. The electric field is going to be 100.0 volts divided by 0.075 meters. If you divide 100 by 0.075, you get 1,333. So I'm going to say that's 1.3 times 10 to the 3 volts per meter. And that's the new unit I was telling you about for the electric field. The electric field has units of newtons per coulomb, but now you see it's also 1 volt per meter. So that's another handy thing. Anybody have any questions on that one? So let's try another example. Whoa. Let's not try it with that on. This is 23-4, say. In this one, we have a charge conducting sphere. So what we're going to imagine is we have a charge that's spherical, like this, and it has a radius R0. And what they'd like to know is what is the voltage, assuming it has a charge Q, what is the voltage everywhere? So what I'm going to do is put this at the origin of a coordinate system. This is going to be my y-axis. Coming out of the page is going to be my x-axis, and then going up, but still in the page, is my z-axis. And what I'm going to do is I'm going to imagine, because the electric field, for this one, we're saying, what is the electric potential okay, that potential is not going to fit there, at all R. Okay, so they're wanting to know what is the electric potential at all the various R's that are possible. My solution is going to require me to understand some stuff. So one of the things I understand is delta, I meant to say delta V and I wrote delta U. Delta V is equal to the negative integral of E dot dl, like that. Okay, and I also know that the electric field, due to a spherical distribution of charge, is given by Q over 4 pi epsilon naught R squared, and it points radially outward, so I can make it a vector by writing it with an R hat next to it. And I'm going to say this is for R greater than R equal to R0. In other words, this function, this electric field, is not true when you get inside of the body. We'd have to work out some details with that, but specifically what we have here is a charged conducting sphere. Oops. Okay, so it's a solid sphere made out of like aluminum, and it's charged with a charge Q, and it has a radius R0. The fact that it's conducting tells us something specific. Specifically, remember, in electrostatics, which is all we're studying right now, we are not examining charges moving through a wire. So since the conductor is what this thing is made of, it has electrons free to move around the body at all times. So if there was electric field at all inside of the sphere, then the electrons would be moving, and that would be a violation of electrostatics. So what we're trying to do is imagine this as if there's no current flowing, and all the free charges have found an equilibrium position, so that they're only moving as a result of thermal quantities. In other words, the temperature is causing them to vibrate and stuff, but that's it. Because of that, there's no electric field inside of a conductor in electrostatics. So what I'm going to do is I'm going to imagine a line coming from the center of the sphere, because we know this, we know that the spherical distribution of charge acts just like a point charge at the origin, as long as you're not closer to the origin than the outside surface. Okay. And what I'm going to do is imagine that initially I'm at a RA, and then I'm going to move in to some RB, like that. So I can now compute this. I can say delta V, which is equal to VB minus VA, is equal to the negative integral of q over 4 pi epsilon naught r squared r hat dotted with dl. Now, last time I chose dl to indicate the direction I'm integrating. I think I'm going to do that again. So I'm going to say this is negative dr r hat. So that negative shows that I'm going from RA to RB. So that's the direction of integration. Now, because I've chosen to do that, that means the range of integration should go from small number to large number. So the range of integration has to go from RB to RA, because that's just the default mechanism. So when I do this, you can see, for instance, that the q over 4 pi epsilon naught and the two negatives come out in front. So I'm going to put positive q over 4 pi epsilon naught. And now what I have is the integral of r to the negative 2 dr, again, using the linearity of the dot product, gives me r hat dot r hat, which is just 1. So now I've got the actual answer is the integral of r to the negative 2 dr. That is r to the negative 1 times negative 1. So I'm going to go ahead and say negative q over 4 pi epsilon naught times, again, we're going from RB to RA. So I'm going to do 1 over RA minus 1 over RB, like that. Does everybody follow what we're doing there? Now, I want VA to be 0. To assign VA equal to 0 as RA approaches infinity, then what we get is delta V, which equals VB minus VA, but VA is going to 0. Now, that turns out to be, since we're taking the RA and we're taking the limit as RA approaches infinity, we can see the 1 over RA is going to go to 0. So now I have a negative 1 over RB times negative Q over 4 pi epsilon naught. And ultimately, my result is Q over 4 pi epsilon naught R. And then finally, of course, that's RB. So that's what the voltage is relative to infinity. I can write it like right here. Delta V equals V of R. And I'll say relative, oops. To infinity. That V of R is just Q over 4 pi epsilon naught R, like that. So for R greater than R0, that's what we're going to get. And in fact, for R equal to R0, that's what we're going to get. So this is part A. And at R equal R0, it's just going to be the same thing. So for part B, V of R0 is equal to Q over 4 pi epsilon naught R0. So that's that. And what happens now is delta V, this is for part C now, for delta V is equal to the negative integral of E dot dl, like that. But if we go from R0 to R less than R0, then the E is equal to 0 because we're inside the conductor. So we're going to get R0 to R less than R0 of 0 dot dl, which just equals 0. So the actual voltage isn't going to change, and that means that C gives us V of R less than R0 is just Q over 4 pi epsilon naught R0, which is what we expect. The entire conductor is a equal potential surface. And that's it. We just finished the, man, I ran over 2 minutes. Sorry about that. But we just finished the example 23.4. We'll finish up this chapter. Remember, I did announce that we're going to try to have a test next week. Again, haven't decided whether that would, it's definitely going to appear next week, but I don't know if it'll be due Sunday or if it'll be due later on the following week. But you guys are free to go. I know Carter had some questions about a test. She can certainly ask those. I might have to take it off a record though, because I still have 2 students that haven't taken the exam. But you're free to go, and make sure you chat me your first and last name if you haven't already. But thanks for coming.
Hey, Mr. White.
Hey, Professor.
Oh,
Yes, go
I'm
for
sorry,
it.
I was just gonna say,
Or whoever,
I
sorry.
have to run to lab, so I'll probably ask you Thursday my questions.
Okay, you can send it to me in a chat too if you'd like.
Oh, okay, cool. Thank you.
All right, you're welcome. Oh,
hey,
Later.
Mr. White, how are you?
I'm all right.
I'm getting ready to go to lab as well. I didn't get the chance to ask you earlier because I was in a patient's room.
Okay.
So I didn't get to a testing center because it's kind of hard right now between my 2 schedules at both institutions and my jobs.
Mhm.
So where or how would you like for me to complete the exam? Because I tried emailing you last night.
You can do an actual, yeah, I saw that. I didn't get to respond to it. I've been too busy. But anyways, you can take it, like I can allow you to use a mirror and do it without proctoring. But there's very specific instructions about that, and you have to get a hold of a decent sized mirror, or you can get someone else like at a local school or something like that, your boss, if you feel comfortable with that dynamic, or someone to actually proctor your test. If you want someone to proctor your test other than the testing center, then you need to get them to send me a text message and include their name, their position, where they work, and also their email address, and I can set it up with them, and then they can watch you while you take the test.
Okay. I don't think my recruiter usually proctors my test, but he's actually in a school right now. He doesn't get back until next week.
Okay.
So I know like last semester I did all of my tests with my mirrors and they were fine. Is that okay for this test or?
It should be fine. It's just the only caveat I tell everybody is if I find anything that makes me feel even remotely suspicious, I make you take it over again. Not because I'm necessarily assuming you're cheating or anything, but I have to assume that if I don't know for certain exactly what's going on. So
Okay.
it'll have very specific instructions. But you say you do have a mirror and a good webcam?
Yeah, I used my full body mirror last semester. Like you can see my whole body and scan the room and whatever.
Okay. Well, if you follow the instructions, you can take it. It's listed on our Canvas page under face-to-face tests, and it's called Mirror. It has the word mirror version in the actual name. That's the one you take. When you're ready to take it, you need to send me a text message. Don't send an email, but send me a text message and tell me that you're in 242 N02B and what your name is, and first and last name, and I will go ahead and set it up for you. But give me like an hour warning, so don't like do it and say, hey, I gotta take this test right now. But
Right,
an hour or
I
two
didn't know
warning,
it was
and I'll
gonna have
put
an
it on.
access code last night, and like I said, they kept me at work, so that was not the plan at all. But I would
Yeah.
definitely do that this time.
Actually, I saw that, and I was thinking you were the other student that was asking me for it. That's actually, but the other student didn't have a proctor, so I was like, I'm not giving you a password. So,
Oh yeah,
but
no,
I'll
like
work that out now.
I literally ran. I was like, my boss was there. We had nobody, and I asked her, and she was like, "Yeah, we could do it on my break." But then it had an access code, and I was like, "Well, I can't actually do it."
Well, if you need to do it tonight or tomorrow or whatever time, just let me know. But I really should be getting it probably by tomorrow or the next day.
Okay,
Okay.
I can make that
Good
work.
luck, Devanya. Let me know.
Thank you.
You're welcome.
Professor?
Yes.
Yes. So I think I was the other student that you might have been talking about. I did have the mirror ready and everything to take it, and I sent a
Okay.
text, but I think it was later in the night and you might have been asleep. I was gonna take it this weekend. I had some issues, and then since
Gotcha.
I work also, I wasn't able to go to a proctoring center.
You have lab tonight though, right?
Yes, sir. But I should be hopefully home around 9,
Okay. And
9:30.
you'll be interested in taking it tonight?
Yes, sir.
Okay. Send me a text message, not an email, but send me a text message. Do you need me to send me my phone number, or can you find it on my syllabus?
I have it from your syllabus.
Okay.
I don't know if you go to sleep early or not. Just wanted to make sure
Oh,
it
no.
wasn't, if I texted you around 9 or 10, it wouldn't be too late.
No, that's not a problem. I just need to get that text from you. When I get it from you, I'll send you an updated password of your specific password. Just don't share it with anybody.
Okay, perfect. Sounds good.
Okay.
Thank you.
No problem. Good luck.
Thank you.
Hey, Hannah, you need me, huh?
I just had a question, and Scott, Mr. Scott might have already sent it to you. My not my equation sheet, but like my work for my equations. Did he already send that to you? Did you want that?
You didn't have to have it this time, but it is helpful, so I appreciate it. Also, if you had an equation sheet, I needed a picture of that just to make sure you didn't, sneak anything suspect in there.
No, I just used the one at the bottom of the test.
Okay. That
So-
works. Yeah, that's not a problem. Yeah, don't need it. But like I said, I think I did get it, so you're good.
Okay. Alrighty. Well, thank you.
You're welcome. Have a good one, Hannah.
You too. Bye bye.
Bye-bye. And that looks like that's it. I'll stop sharing the screen, and bye-bye, everyone. Bye-bye. It's been real.